Good morning. My name is Sangeeta Beal. I am working as an assistant professor in the Department of EC, Vivekananda College of Engineering and Technology, Puttur. So today we are going to study about the experiment, that is, you can see Class C tuned amplifier. So this is mainly used or mainly based under the use of IFT, that is called as intermediate frequency transformer. So usually we know amplifier is nothing but which is used to increase the or strengthen the signal of a strengthen the power of a signal or increase the power of a signal. So as we know, there are many number of amplifiers used or amplifier classes used like class A, class B, class C, which mainly gives an output based on the conduction angles. I will tell you why we are going for class C amplifier. So here we are using a class C tuned amplifier. So tuned we know it is nothing but which is making the usage of an C as well as that is your capacitance as well as the inductor. So based on this tuned transformer or intermediate frequency transformer, you are going to tune the frequency which will give a maximum frequency at some particular frequency or particular value. So that particular value of the signal will give you a maximum voltage, which is nothing but the amplified voltage. So this is actually the circuit or the circuit block diagram. So you have to apply a carrier signal of 1 volt peak to peak. So which will be, when you get the output, you get the amplified output across the IFT or intermediate frequency transformer. So imagine the designed value of this intermediate frequency, it is 455 kHz. So when you draw a graph, that is, so starting from the frequency where we are getting, usually we take from 150 Hz or 150 kHz. So starting from 150 kHz, so at particular frequency, if I take it as 455 kHz, we are getting the maximum carrier frequency. So the expected graph will be frequency as well as the gain, which we calculate through a formula, that is 20 log V0 by Vin. V0 is whatever the output we are getting across this IFT, and Vin is nothing but the carrier signal input which we are taking as 1 volt peak to peak. So now we can see this generation of this class C tuned amplifier output through the CR. So you can see that, as I have told you, amplifier is what? It is a signal or a device which is used to strengthen the signal. So here if you take the amplifier classes, it is mainly divided into class A, class B, class AB and class C. Actually the amplifier classes, it is divided into two modes, A, B, C and D, and still you have other classes, that is E, F, G, all those things. But still this is only restricted area until this class C. I will consider only the class A, class B, class AB and class C. So class A, if you take, the description is it can conduct for full cycle, that means 360 degree, which mean to say that if you apply a waveform, there is a full conduction of a signal where theta you get, that is 0 to 2 pi. So if I take the next class, that is class B, it is having a description that your half cycle will be conducted, that is theta is equal to 5, which will have a form that is this much, only the half cycle is conducted. Now if you take the next class, that is class AB, it is slightly more than 180 degree, which will have the theta range, that is theta is greater than pi, less than 2 pi. That means your signal will be somewhat like this. So it will have the conduction but not conduction until 2 pi. And the last one is class C amplifier, that is which is having slightly less than 180 degree where theta is less than pi. So which will normally have the form 0, if I take this pi, so 0, in between the 0 and pi the conduction is obtained. That means you can see that in the class A and class C amplifier, the input signal which you give as a full sine wave, whereas the output which you get across the output, that is not a full input signal. So that is the disadvantage of your class C amplifier, that is the conduction angle is very less. So conduction angle is very less, which means to indicate that your distortion in the class C amplifier is more. So since the conduction angle in the distortion is more, there is a relation in order to define this distortion as well as the conduction. So if I take this class Li, as I have said you, it will conduct less than 50% of an input signal. So since I have the distortion is high, but efficiencies are also high. Whereas when you consider this class C amplifier, even though the distortion is high in the class C amplifier, the efficiencies you get in the class C amplifier is around 90%. Now there are two modes of operation in case of this class C amplifier. One is your tuned class C mode of operation, other one is your untuned mode of class C operation. So we'll first see what is an untuned operation. So untuned operation is nothing but which is not having the involvement of your inductor as well as capacitor. So that is nothing but, you can see here the figure, there is a transistor given, you apply the input signal, whereas instead of connecting a inductor or capacitor, you are directly connecting a load. So this is nothing but a load which is connected here. So this load which is connected here, so this forms an untuned amplification which will give you the output. So you can see there is no full output obtained across the untuned amplification. Now we are going for tuned amplification. So if you take the tuned amplification, so tuned amplification is nothing but you have a capacitor and you have a inductor which is nothing but your IFT. So if you take this capacitor and inductor, so this mainly depends on the value of the inductor, that is C will have a fixed value, that is 2200 picofarad. So it is already decided when you design the IFT, that is 2200 picofarad. Whereas L is nothing but you have to tune the frequency. So in the IFT there will be a screw given. So when you turn the screw, the L value changes because of the air core gap between the device or the IFT which you consider. So when that air core gap changes, the inductor value will change, which will tune the frequency, and at particular one frequency which we considered as FC, or if we considered it as FIF, which is called as intermediate frequency, you will get the frequency where you get the maximum output voltage. So there are two advantages of using this tuned amplification. So one is that you can get the desired frequency or the carrier frequency, that is the intermediate frequency, using the tuned amplification. Other one is the output across the amplification which you get is that full input signal which you give. Across the output there is an amplification of a signal as well as the input signal. As an input signal, the output is retained. So using this tuned amplification, the disadvantage of your untuned amplification can be overcome. That is, one is you can get the desired frequency, other one is the output which you get across the IFT is an amplified one, as well as you get the full input or full output as same as your input signal. So this is the operation of your class C amplification. So now we will see how to take the readings using this experiment, that is your class C tuned amplifier. So you can see in the figure or circuit, see how I have connected this circuit. So this is the transistor which we use, that is BC107, and this is called the IFT which you can see. So this IFT, that is your intermediate frequency transformer. So why this intermediate frequency transformer is used? Because by using this intermediate frequency transformer, you can tune for a particular frequency. So if I say, so this is designed for 455 kilohertz, it will give you in the range of 200 to 455 a particular frequency. So whatever the frequency you desire, so that frequency can be obtained from this intermediate frequency transformer, whereas the rest of the frequencies will be suppressed. So you can see here inside this IFT there is a screw actually. So this screw which you can see here, you can tune this by using a driver or something. So when you tune this screw, there is an air core gap in between the screw. So which will change your L value. So based on that L value, you can get the intermediate frequency. So BC107, which will have the emitter, base and collector as your terminal. So we are using a 3 resistors. One is 5.6 kilo ohm, other one is 120 kilo ohm and another one is 150 kilo ohm. So 2 capacitors, one is 0.01 microfarad, other one is 0.1 microfarad. So this intermediate frequency, we are not showing the capacitor here because inside it only your 2200 picofarad capacitor is inbuilt. So using a power supply, having a constant power supply, that is a 12 volt, and your CRO, this is a signal generator. Now set the frequency initially to some 100 Hertz, 100 kilohertz LV, or you can keep some 150. So input voltage, you can see here I have set it to reduce the amplitude and keep it to 1 volt peak to peak. Okay. So now it is 1 volt peak to peak. Now see the output waveform. So you are getting some output signal. So in this, start varying the input frequency of your signal generator, that is your carrier signal. So at some particular point you can see the amplification. So now it is reducing. I'll start increasing the frequency. So it is around 200 now. Increase, increase, increase. So you can see there is an amplification occurring. Increase, increase. See, after this point, that is you are getting some maximum at 272 kilohertz. After that, if I increase the frequency, there is again a reduction. So that means I am getting the intermediate frequency at a range that is 272 kilohertz. That means the intermediate frequency FC is 272 kilohertz. So now I have to take the reading. So there is an observation table. So I will start taking the reading from 240 or 245 I will start. So I need a frequency. So this is the observation table which is having an input frequency in hertz. Output signal is nothing but whatever the amplitude you are getting, and gain in dB. So if I take the input frequency, I will start from first reading, that is 245 kilohertz. So see, check the amplitude across your output signal. It is around, so each point will take 0.2, so it is 1.2. 1.2 into 1 will give you 1.2 volt. And next I will take the reading for 250. So 250 it is again 1.3. 250 kilohertz, it is 1.3 volt. Again increase the frequency to 300 or 260. 260 it will give you, it is 2.2. So 260 kilohertz, 2.2. So before that we'll take the reading for 255 also, so that it will be easy to plot the graph. So it is 1.6. So 255 kilohertz will give you 1.6 volt. So now again increase to 265. So 265 it is 3.4. 265 kilohertz, 3.4 volt. Next it is 270. So 270 it is 5.2. 270 kilohertz, 5.2 volt. Now since we were getting around 2.72, I'll see for 2.72 also it is same. There is a decrease. That means we can say that 2.70 which you use, 270 kilohertz, that is your intermediate frequency. Again take for 275. So it is 4.6. 275 kilohertz, 4.6 volt. So there is a reduction. Again take for 280. So 280 it is 123.4. Again 290. It is 1.8. 1.8 volt. Before that we'll take for 285 also. 285 it is 1.4. 2.4. So like this you can take until, so again if I take 295, 295 is 1.4. So 295 kilohertz, it is 1.4 volt. Again 300 kilohertz is 1 point, again it is 4 volt. So if I increase again, so see again there is a decrease. So 300 it is, so 305 it is 1.1 volt. So you can see from this, so starting it is increasing and then at particular point that I can say 270 kilohertz, it is 5.2 volt, which is the maximum amplitude. Again there is a decrease. So my intermediate frequency is nothing but 270 kilohertz. So now you need to calculate what is the gain. So gain formula is 20 log V out by E. So using the calculator you calculate the value 20 log. So V in is right here. V in you are taking 1 volt peak to peak. So it is nothing but 20 log 1.2. So which will give you a gain 1.58 dB. Again it is 20 log 1.3, which will give you 2.27. So do similarly for all the values. It is 4.08. Again 20 log 2.2 will give you 6.48. 20 log 3.4, so this is 10.62. 20 log 5.2 will give you 14.32. 4.6 is 13.2. 20 log 3.4 is 10.62. 20 log 2.4 is 7.6. 20 log 1.8, that is 5.10. Last value 20 log 1.4, 2.9 in 2.9. 20 log 1 will give you, this is 0. So you have to plot the graph now for this. So take the y-axis as gain in dB and your x-axis as frequency in kilohertz. So this is the output graph which you can show. So start from the frequency 245 itself. So 245, 250, 255, 260, 265, 270, 275, 280, 290, 300, 310. So initially, what is the value? I can take the gain and dB here starting from 0. So it will start from say 270. So if I take this as 245, 50, 55, 60, 65, 70. So this is my intermediate frequency. So I am getting a maximum gain of 14.32. So this is the output graph which I have to plot after you do the experiment. So you know how this is done. So last is you have to see, or before the experiment you need to know what is the calculation, how to calculate the L value. So usually we know a quality factor, which is nothing but carrier frequency divided by the bandwidth. So if I take the carrier frequency, that is intermediate frequency, bandwidth is nothing but your upper side or USB, upper sideband minus your lower sideband. So quality factor, intermediate frequency, we have taken it as, so intermediate frequency is given by an equation, that is 1 by 2 pi root LC, which is nothing but you are using through a tuned frequency. So you have seen the tuned circuit, so that is having a formula that consists of 1 by 2 pi root LC. So C we have chosen it as 2200 picofarad. Intermediate frequency, it is designed for 455 kilohertz. Substitute these two values in this equation. So I will get root L 1 by 2 pi FIF root C. L is equal to 1 by the square root of C. Substitute Fi intermediate frequency as 455 kilohertz, C as 2200 picofarad. So you will get a value 55 microfarad. So whichever the IFT now we are using, so that is tuned to a frequency that is 455 kilohertz, having the L value as 55 microfarad. So I can say at last that using a class C IF tuned amplifier, you can find the frequency whichever you design. So here we have designed it for 255 kilohertz. We are getting the intermediate frequency using this experiment as 270 kilohertz. So using this, you can select a particular frequency whichever is required or desired frequency, whereas suppress the other frequencies. So this can be done using your intermediate frequency transform. Thank you.